So in this video, we are going to look at using implicit differentiation in order to find dy over dx, so the derivative of y with respect to x, for equations that have trig in them. And remember, we use implicit differentiation when we have an equation where we can't explicitly solve for y. So we can't get y by itself on one side of the equation and then its rule in terms of x on the other side of the equation. And I gave you a basic example, little refresher of implicit differentiation here for the equation x squared plus y squared equals to 1. So same steps as before, where our first step in differentiating with respect to x is going to be to make that statement that we are differentiating with respect to x. So for each term, so I'm going to write d over dx of sine of x, and that means we're differentiating sine with respect to x, d over dx of y, and d over dx of cosine of y. So this is just the statement. This line states that we are differentiating with respect to x. So going from left to right, thinking chain rule, okay, we think of sine as being the outside function and the x as being the inside function. So if we're thinking derivative of the outside, derivative of sine is cosine. We leave the inside alone, and then if we multiply by the derivative of the inside, that's the derivative of x with respect to x, which is just 1. Or you can write dx over dx if you're more comfortable with that. And then the derivative of y with respect to x is dy over dx. And to differentiate cosine of y, we're going to think of cosine as being the outside function and y as being the inside function. So thinking chain rule, the derivative of cosine would be negative sine. We leave the inside alone, which is y. I don't know why I left so much space. And then times the derivative of the inside would be the derivative of y with respect to x, which is dy over dx. Okay, so we've differentiated. Our next step is to get the terms that have dy over dx on one side of the equation and then all the other terms on the other side. So I'm going to move the terms that have dy over dx over to the right-hand side just because it's less steps, but it doesn't matter. You can do either side. So I have minus sine of y times dy over dx minus dy over dx. And now we're ready to factor out the dy over dx on the right-hand side. So when I factor dy over dx out, I'll have negative sine of y minus 1. And to finish getting dy over dx by itself, we'll divide by negative sine of y minus 1 on each side, leaving us with cosine of x over negative sine of y minus 1. And I like to put the parentheses. It's not necessary, but I like to put the parentheses around the arguments of the trig functions just so it's very clear what is the argument. So then that is dy over dx, so the derivative of y with respect to x for this first example. Okay, next example. First step, again, I'll just stick with green, is going to be to state that we're differentiating each term with respect to x. Looks like we're going to have lots of product rule in this equation for differentiating this equation. Okay, so we have a product, right? We have x times sine of y, meaning we need to use product rule. So first factor times the derivative of the second factor. And to find the derivative of the second factor, remember we need to think chain rule. So sine is the outside, y is the inside. So the derivative of sine is cosine. We leave the inside alone, which is y, times the derivative of y with respect to x, plus the second factor, which is sine of y, times the derivative of the first, which is just 1. So that's the derivative of that first product. I'm going to move this over a little bit. And then minus, and I'm going to use brackets to group my product rule for y times cosine of x. So first factor times the derivative of the second factor with respect to x would be negative sine of x. Plus the second factor times the derivative of the first. Okay, which would be dy over dx. So just to review this again, I have the first factor times the derivative of the second factor. Now, because the second factor, cosine of x, the argument is x. So if you think chain rule, derivative of the outside would be negative sine, leave the inside alone, which is x, times the derivative of the inside would be dx over dx, which is 1. So that's why, since I was differentiating with respect to x, I just stated what the derivative was. And then plus second factor times the derivative of the first factor. Okay, equals, and the derivative of the constant 2 will be 0. So I'm going to clean this up. I'm going to distribute the negative to each product in that sum that's in the brackets. So we'll have x times cosine of y times dy over dx and then that will be plus sine of y plus y times sine of x minus cosine of x times dy over dx equals 0. So since both terms that have, so both of the products here, let me use a lighter. So since both of the products that have dy over dx are on the left-hand side, I'm going to move sine of y and y times sine of x over to the right-hand side. So on the left, we'll have x times cosine of y times dy over dx minus cosine of x times dy over dx. And I realize that some of you guys might be to the point where you can just factor out the dy over dx in this same step. And if you are confident doing that, go for it. Let me move this over. Okay, so factoring that dy over dx out on the left. And now we're ready to finish isolating dy over dx. Let me just shrink this a little bit so that everything fits nicely in the box I have. Okay, so dy over dx, derivative of y with respect to x, is negative sine of y minus y times sine of x divided by x times cosine of y minus cosine of x. And the last example that I have on here. Okay, first step is to show that we're differentiating with respect to x. Okay, so thinking chain rule, tangent is the outside function, x plus y is the inside. Derivative of tangent is secant squared. We'll leave the inside alone, so I'm writing x plus y as the argument. And then times the derivative of the inside. I'm going to use brackets to organize that since it's the derivative of a sum, would be 1 plus dy over dx. Okay, and then the derivative of tangent of x with respect to x. So since it's with respect to x, that's just going to be secant squared of x, right? Because it would be times dx over dx, or times 1. And derivative of tangent, so again, tangent is the outside, y is the inside, so derivative of the outside, leave the inside alone, times the derivative of the inside with respect to x. Before we can get all of our terms with dy over dx on one side of the equation, we need to distribute the secant squared of x plus y. So that'll be secant squared of x plus y plus secant squared of x plus y times dy over dx equals, I guess I could copy and paste the right-hand side, huh? Copy, paste. There we go. And, gosh, I'm going to get the terms of dy over dx on the left-hand side just because I like my final step to have dy over dx on the left side. So I'll have secant squared of x plus y times dy over dx minus secant squared of y times dy over dx. And again, if you're able to factor out the dy over dx in this step, go for it. Oops. Factoring the dy over dx out. I'm going to use the copy and paste just to cut down on the video time. Okay, so then when we divide by secant squared of x plus y minus secant squared of y on each side of this equation, we'll get dy over dx by itself. Okay, so there is dy over dx for this equation. Forgot to highlight the second one. So these were a few examples, differentiating equations using implicit differentiation that have trig in them. And you'll notice that I only have sine, cosine, tangent in these equations and in the practice that you're doing, and that's because those are what we're going